Hello, I'm going to introduce the next block of videos that I'm going to be recording, which are on quantum physics and relativity. And I know these are two separate topics, but I'm not going to be doing a lot of videos on these. So I thought I'd just do the one intro to cover both. But they are connected with the fact that both are stepping outside of classical physics. We're going to take some more tentative steps into modern physics. And this isn't our first foray into modern physics. In the structure of matter section, when we were looking at particle physics, nuclear physics and such like, we were moving into modern physics there. But yeah, quantum physics and relativity very much into modern physics again. What we're looking at here in these is tackling the very small in quantum physics, the very fast in special relativity, and the very massive in general relativity. So we're looking at very small, very fast, very massive. And as I've been saying through so many of these videos, it's under those extreme circumstances that classical physics starts breaking down and is no longer accurate enough to describe what's actually happening in the universe. So this is why we need these new descriptions when we get onto these extreme scales of size or speed or mass. And we've walked a historical path to this point already. We've spoken about Maxwell's equations, which unified light and electromagnetism in 1873. That's when those were published. We then went through J.J. Thomson and his discovery of the electron in 1897. We've been through the Millikan oil drop experiment that was, 1910, 1911. So there was a lot of interest being developed, particularly in electrons and other subatomic particles. The interaction between light and matter, waves and matter. And this resulted in a number of groundbreaking discoveries at the start of the 20th century that really ushered in modern physics in all of its weird and wonderful ways. So on the quantum side, there's the particle nature of light, as we see in the photoelectric effect, and there's the wave nature of matter, as we see in things like diffraction of electrons. So this is two sides of what we call wave-particle duality. So I'll be talking about that. Then we've got other strange behavior as well. Things, described by, say, the Heisenberg's uncertainty principle, Pauli exclusion principle, quantum entanglement. Strange behavior at these very small scales, these subatomic scales. I'll try and unpick some of that. I'll bring in things like electron microscopes, and things that we could exploit at this very small scale, and understanding of quantum physics. So that's what I'm going to be looking at from the quantum side. On the relativity side, the Michelson-Morley experiment that struck a blow to Newtonian mechanics, and it opened the door to Einstein and his theories of relativity. First special relativity, and then general relativity. So I'll get into the difference between special and general relativity. This brought in, with special relativity, which came first. I mean, straight away, you had these mind-bending ideas around time dilation. So, time changing depending on your motion, time moving differently for different observers. So we've got time dilation, we've got length contraction, we've got the relationship between matter and energy, encapsulated in his Einstein's famous E equals mc squared equation. So trying to unpick some of those ideas, at least as best we can, before we have the maths available to us to really get into the weeds of it. But in terms of our pre-university physics, there's still some good ground we can make looking at those ideas. I look at things like the twin paradox and how that gets explained with these ideas around time dilation and length contraction and such like. And then I'll sum up with a little bit on general relativity, not a lot, because it's a bit more beyond us than special relativity is. We can get fairly meaterly involved in special relativity before we head off to university, but general relativity is a little bit of a different matter. But I'll at least try and say something about it towards the end of these videos. So that's going to be the basic path. It'll be quantum physics first, then relativity, doing what we can while avoiding the detailed maths that we're not really ready for yet. But yeah, this is going to be, by the time I've thrown in a few practice questions as well, maybe sort of 15, 20 videos, something like that. So hopefully it'll still be fairly substantial, even though we've got limitations of what we can look at the moment.